This is the second video on integration by parts. So before watching this video, you should make sure you're comfortable using the formula that you're seeing on the screen. In the first video, we derived that formula and just kind of worked on the mechanics of how exactly we use that in a problem. So what we want to start looking at is, how do you know, first of all, when to use integration by parts? And then once we're going to attempt integration by parts, how do you choose what u is going to equal and what dv is going to equal? Unfortunately, for both of those questions, they're not definite answers. So it's not like you can say, oh, we always use integration by parts on this problem, or that you always let u equal this and dv equal this. There aren't definite answers to those questions, but there are things that you look for, and they're things that you try when you're doing the problems. So let's talk about this problem. This is similar to problems that we did on exam or on the video before this. So let's say I've got x e to the 3x dx. And so a good way to generally approach integrals is to think of it as in this order. So like the first thing you might think of is the integral a basic form, meaning one of the 11 basic forms that we talked about at the very beginning of the course? Or is it one where you can do some quick algebra or quick trig in order to make it into just basic forms? And you cannot on this problem. The second thing that in most cases you would want to consider is maybe u substitution would work. And so here, one thing that might work is to let u equal 3x. I think it doesn't work real well in this problem, but if it was like 3x squared in the exponent there, then u equals 3x squared would work well, because du would be 6x and the x is sitting there. Here, there's not probably a good u substitution to work, so then the next thing that we might think to try is integration by parts. And so that does happen to work on this problem, but that's what we're going to try next. That's kind of a general approach that works on a lot of integrals, not every single time, but this is something that you can think about doing on or when you're approaching an integral in general. So basic forms, and then u sub, and then parts. Okay, so once we decide we're going to try to do parts, we want to look at what happens within the integration by parts formula. So when you start with the problem that you have is u dv. So you have the integral of u dv, and u could be any part of that problem, dv could be any part of that problem, and dv will include dx. The important part is that u times dv needs to be the entire problem that you're currently dealing with. Once you apply integration by parts, then you have this new integral to deal with. And the key is that that integral is an integral that we can handle. Hopefully it's a basic form. If not, maybe it's u substitution, or maybe it's parts, or later maybe it's something else. The uv part of the answer, that you need to have in the answer, but you're basically done with that after the first application of integration by parts. So you're not going to do anything else with that part other than maybe simplifying. The key part is this new integral. And so you want to get an integral that you can handle at that point. And so what you want to think when you're looking at a problem like x e to the 3x, no matter what I do, if I go from u to du, which is what's going to happen when I go from the left-hand side of this equation to the right-hand side of this equation, I'm taking the derivative. So you take the derivative when you do that. And when you go from the left-hand side to the right-hand side, you go from dv to v, which means you're taking the antiderivative. And so one guideline to think about, or one thing to think about when you're choosing what u should equal and what dv should equal, you think about what's going to happen when you're getting the new integral. So let's look at problem one. Probably the two most logical setups would be to say either let u equal x and let dv equal e to the 3x, or to let u equal e to the 3x and to let dv equal x dx. And there should be a dx over here on this dv. Okay, and so let's think through what's going to happen. So if you choose this first setup, if u is x, then du is going to be 1 dx. And so du would be 1 dx. And if dv is e to the 3x, v is the antiderivative of that, which is 1/3 e to the 3x. And so v times du in that case would be e to the 3x times dx, which is a problem that we can handle. If you do this, if you do the setup on the right, du is then e to the 3e to the 3x dx. V is 1/2 x squared. When we multiply v times du together, we get a coefficient outside, but we get x squared e to the 3x, which is harder than the integral that we started with. Okay, so looking at the integral to begin with, we think, okay, if I take x, I'm either going to take its derivative, which would mean x is going to go away, or I'm going to take its antiderivative, which means x is going to go up a power and become basically x squared. When I use e to the 3x, if I take its derivative, it's going to stay e to the 3x with a coefficient in front. If I take its antiderivative, it's going to stay e to the 3x with a different coefficient in front. So no matter what, e to the 3x is going to be in the new integral. And so if we're going to have e to the 3x there, we want to think, do I want to keep x squared, or would I rather drop an x off? And so we want to get rid of the x, which means we're going to use this first setup. Okay, so let's work the problem. So here, we're going to use this setup, u equals x, dv equals e to the 3x dx. So we get uv. When I multiply uv together, I get 1/3 x e to the 3x minus v du. So I pull the 1/3 out, and I get the integral of e to the 3x dx inside. Now that's 1/3 x e to the 3x minus 1/9 e to the 3x plus c. That's 1/9 because that last integral would be a quick u substitution where u equals 3x and du then would be 3 dx. So you multiply inside by 3 and outside by an additional 1/3. Okay, so that works well on that problem. Let's look at a second example. So if I have the integral of x squared natural log x dx, if we think through the kind of three types of problems we know how to do, basic forms, u sub, and integration by parts, we should probably pretty quickly figure out this is not a basic form, and there's not a quick simplification we can do to make it into basic forms. You can mess with a couple things for u substitution, but it's not likely to work well. And so then we're going to consider parts. So then the idea is we're probably u is going to be x squared, or u is going to be natural log x. dv will be the other part. So we're going to take the derivative of one part, we're going to take the antiderivative of the other part. So either x squared is going to become 2x, so basically just x, or x squared is going to become 1/3 x cubed in the new integral. Okay, and both of those might be okay, depends on what else it's with. Natural log x, if I take the derivative, that's going to become 1/x. And then if we take the antiderivative, that seems like a formula we should have at this point, but we actually don't. And so we don't know how to do that at this stage in the course. So that means we're going to need to take the antiderivative. So if parts is going to work, and we know how to do it at this point, then u is going to have to be natural log x because we know how to do the derivative. We don't know how to do the antiderivative. dv is going to be then x squared dx. And we've got to take the antiderivative of that. This ends up working because when I multiply 1/3 x cubed times 1/x, I get a simple power function that we know how to integrate. And so let's see what happens now. So if u is natural log x, du is 1/x dx. If dv is x squared dx, v is 1/3 x to the third. You should now pause the video and try to complete this problem and then check it with me in just a minute. Okay, so when we do the integration by parts formula, we do uv. uv becomes 1/3 x to the third natural log x minus the integral of v du. So we pull the 1/3 out. When I multiply v times du, I get x to the third times 1 over x, which is x squared. So now that is an integral that we know how to do. So we get 1/3 x to the third natural log x minus 1/3 times 1/3 x to the third plus c. We can simplify that second half, and so we get 1/3 x to the third natural log x, not n, natural log of x, minus 1/9 x to the third plus c. And that's the answer on this problem. Okay, so we're going to continue doing more examples, but that's kind of the thought process on when you would use parts and how to pick u and dv. There's, again, not a definite way to do that every time, but those are some guidelines that can help. Okay, so I actually want to look at the antiderivative of natural log x dx. So we said just a minute ago that we actually don't know how to do that, which is true. We've not covered that in this course, and doubtful that it was covered in Calc 1. And so we end up using integration by parts here. This is not a basic form. There's not a useful u substitution to do at this stage. And so we set up integration by parts. It seems weird to do that because there's only one thing in the problem. There's only the natural log of x, and then I guess dx, but there's only one main function in the problem. So the two options are to either let u equal natural log x and then let dv equal dx, or I guess you could let u equal 1 and let dv equal natural log of x dx. And so the first setup would work this way, where if u is natural log x, du is 1 over x dx. If dv is dx, then v is x because it's the antiderivative. Over here, if we did this setup, du would be 0 dx, but still 0. V would be the antiderivative of natural log x, but if we knew how to do that, we would be done with this problem already. So that's probably not a good setup. And so the one on the left will work. When we work it out, we get uv. So uv is x natural log x minus the integral of v times du. Well, v times du is x times 1 over x. That's 1 dx. The antiderivative of 1 is, with respect to x, is x. So we get x natural log x minus x plus c, and that's the answer on this problem. Okay, so that leads to a couple of other problems that work in a similar way. So if you have a problem like this, so let's say I have the problem inverse tangent of x dx. That again is a problem that we actually don't know how to do. So there are two things that you want to be careful about that if you slow down and think about it, you probably know. But when you're doing a test or doing a bunch of problems and working quickly, it's easy to do these two things and they're actually not right. And so one thing is to put 1 over 1 plus x squared. Okay, and that makes sense, but that's wrong because the derivative of inverse tangent is 1 over 1 plus x squared, not the antiderivative. The antiderivative of 1 over 1 plus x squared is inverse tangent, but that's the opposite of what we're trying to do here. So that is not right. The other thing that people like to do here is to say, okay, that's equal to the reciprocal of sine over cosine, and so it's cosine over sine, and that's not the case. That -1, that is not a power. That's an unfortunate notation because when that's like a 2, that is tangent squared, but when it's tangent to the -1, or when it looks like it's tangent to the -1, it's not a -1 power. That means inverse tangent. That is something that we should understand from trig. If not, maybe that's something we could review outside of our videos. That's something worth understanding. But this is inverse tangent, which is something completely different from -1 power. So you don't treat that as a power at all. So then if you look at what we've got, we say, okay, is this a basic form? And it kind of seems like it is, but it's not. And then there's not a u substitution that works well. So then we try parts. And so the same deal as above, if we're going to try parts, really the only thing that would make sense is to let u equal inverse tangent of x and to let dv equal dx. Any other setup would require us knowing the antiderivative of inverse tangent x, and we don't know that or we wouldn't be doing this to begin with. And so if u is inverse tangent x, du is 1 over 1 plus x squared dx, and that is right because it's the derivative of inverse tangent x. If dv is dx, v is x. And so we do uv, so we get x inverse tangent of x minus the integral of v du. But when I multiply those together, I get x over 1 plus x squared and then dx. On this new integral, that's not a basic form, but we can do u substitution, where u is 1 plus x squared, du is 2x dx. And so we've got x inverse tangent x just carrying through, minus, we're going to move the x off of the fraction. We're going to put that next to the dx. We need a 2 here, and then that means we need a 1/2 outside. So we get x inverse tangent x minus 1/2 integral 1 over u du. That's then the natural log of the absolute value of u. And we get x inverse tangent of x minus 1/2 log of 1 plus x squared plus c. It's okay to drop the absolute value because we know that 1 plus x squared has to be positive. And so this is the antiderivative of inverse tangent x. Okay, we're going to work one more problem. So I'd like you to pause the video and try this problem. But let's do the arc sine of x. Oh, we're going to do 2 more problems. I'm sorry. So pause the video and do arc sine of x dx, and then we'll work it together in just a minute. Okay, so on this problem, we're going to follow a similar pattern to the last 2. So we're going to let u equal inverse sine or arc sine of x. dv is going to equal dx. du is 1 over the square root of 1 minus x squared dx, and v is x. uv is then x arc sine of x minus the integral of x over the square root of 1 minus x squared dx. On this integral, we're going to let u equal 1 minus x squared. du is negative 2x dx. This is for u substitution, not parts. So we get x arc sine x minus negative 1/2 integral 1 over the square root of 1 minus x squared times negative 2x dx. That gets us x arc sine x plus 1/2 times the integral of u to the negative 1/2 du. U to the negative 1/2 because it's 1 over the square root of u. That's x arc sine x plus 1/2 times 1 over 1/2 u to the 1/2 plus c. That's x arc sine x. The 1/2s cancel, and we get plus 1 minus x squared to the 1/2 plus c. If you wanted to rewrite that as a square root, you could. And so we get that for arc sine of x. Okay, let's look at another problem. I may have lied. We might do 2 more problems on this video, but on this problem, we're going to do the integral of e to the x sine x dx. And so on this problem, quickly, it is not a basic form. There's not a good u substitution to use, so we're going to try parts. The 2 obvious things to try are to let u equal e to the x and let dv equal sine of x, or to flip it around, and so let u equal sine of x and dv equal e to the x dx. In either case, whether we let e to the x be u or dv, you're going to take the derivative or the antiderivative, and in either case, you're going to get e to the x. When you do sine x whether you take the derivative or the antiderivative, you're going to get cosine x, either with a negative or without, but you're going to get cosine x. As you continue to apply integration by parts, that's going to cycle sine, cosine, cosine. What that means is that this is not going to matter which setup we choose. So I'm going to choose for u to equal e to the x and dv to equal sine x dx. So if u is e to the x, du is e to the x dx. If dv is sine x v dx, then v is negative cosine because it's the antiderivative. So we start with integration by parts. We do uv, that's negative e to the x cosine x, minus v du, well that's minus negative, so it's plus, the integral of e to the x cosine x dx. Now that integral is very similar to the first integral, and it's a little weird, but it should be somewhat clear that if we do parts again, we're going to get back to the integral we start with. And so let's do that again. We're going to let u equal e to the x. We're going to let dv equal cosine x dx. Du then is e to the x dx, and v is positive sine because we're taking the antiderivative. So we get negative e to the x cosine x plus the integration by parts formula. So that's e to the x sine x minus the integral v du, but that's e to the x sine x dx. That integral is the same as the integral that we started with. So when that happened, we stop with that line of work. So we say, okay, let's stop and let's write out what we've figured out. So what we figured out is that the integral of e to the x sine x dx is equal to that very last line. So that's equal to negative e to the x cosine x plus e to the x sine x minus the integral of e to the x sine x dx. We're now going to use that equation to solve for the integral. So the coefficients of these integrals are 1. And so what we can do is add the integral on the right to both sides. So that would get us 2 integral e to the sine x dx equals negative e to the x cosine x plus e to the x sine x, and there might be a constant left over. We can put that here or on the next line. It's important to note, though, that what we're doing is adding it. So if this had been minus 3, then when we add it over, we would get a 4 here. If it had been plus 2, we would subtract it over and get negative, oh, sorry, if it had been plus 3, we'd subtract it over and get negative 2. And so you're moving it over to the other side, and that means that we're going to get a different coefficient depending on what the coefficients were. Now we're trying to solve for the original integral. So we divide by 2 or multiply by 1/2. So we get the integral of e to the x sine x dx is equal to negative 1/2 e to the x cosine x plus 1/2 e to the x sine x. And there could have been a constant mixed into those antiderivatives the whole way through. And so this is a little weird, but it's something worth practicing. And so you'll see on the worksheet several of these. When the coefficients of the x's are 1, it's relatively straightforward once we get used to this. You will see problems on the practice where the coefficient here and the coefficient here is not 1. The process is still the same when that happens, but it gets a little more tedious. And so rather than doing one on the video, I'm going to let you try that on the homework and then check it versus the solutions that you've been provided. But that is it for this video. In the next video, we'll look at some more complicated examples where we combine integration by parts with u substitution. All right, thanks for watching.